Welcome to the online training, Intel Quartus Prime Software Hyper-Aware Design Flow. My name is Marlon Price. This training is one in a series of online courses that will show you how to design for Intel FPGAs that contain the Intel Hyperflex architecture. While design structures targeting traditional FPGA fabrics are fully supported, to take full advantage of the Hyperflex architecture, certain device and tool features will need to be utilized. This training focuses on one aspect of that tool flow, what we call hyper-aware design. By the end of this training, you will be able to describe the Quartus Prime software support for enabling and analyzing the use of hyper-register resources in the Intel Hyperflex architecture. In the course of this online training, we will first cover what new hyper-aware features have been added to the compilation flow of the Quartus Prime software and how to enable these new features. Then we will learn about some additional hyper-aware tools that can be used to evaluate the results of your Hyperflex architecture design. So we start with the hyper-aware compilation flow. In order to achieve design performance in an FPGA, you need hardware that can reach your target clock rates, and you need software that can make use of that hardware correctly. The Hyperflex architecture is already built for high performance by providing hyperregisters all throughout the device. This gives the compiler many options for where to place registers in order to increase the clock speed. But it would be a lot of work if you were tasked with manually trying to code your RTL to position the registers in just the right location to take advantage of the hyperregister positioning. For one, register placement is almost entirely handled by the Quartus software. Yes, you can use location constraints to position registers in specific locations in the floor plan, but that is not something that you want to do even for a fraction of the millions of registers found in a modern large FPGA. So assuming you don't manually place registers, the typical flow could require many iterations of recoding your RTL to try to get the compiler to map the right RTL register to the appropriate hyperregister location. In some sense, though the architecture makes the faster speeds possible, the work needed to reach those speeds would make the solution completely undesirable. Thus, the hyper-aware software flow is required. To support the use of hyperregisters, the Quartus Prime software compilation flow adds two new hyper-aware features, the Hyper-Retimer module and Hyper-Aware optimizations. Both hyper-aware features run as part of the FITR module during compilation. The Hyper-Retimer is the stage of the compilation flow during which registers in adaptive logic modules, or ALMs, are moved into hyperregister locations. The Hyper-Retimer is on by default in the Quartus Prime software. During the FITR place stage, logic registers are placed in ALMs. Then the Hyper-Retimer comes along afterwards and moves some of the ALM registers into hyperregisters instead to improve performance. The Hyper-Retimer will only run if needed. So if the FITR determines that the results of the place stage already meet your timing constraints, then the Hyper-Retimer will not run. The Hyper-Retimer also supports incremental optimization. Incremental optimization is a feature of the Quartus software that allows you to stop compilation at various points, review the results, and make decisions or changes. Depending on what you changed, you can continue on in the flow or you can start over. The advantage is that no longer do you have to wait until the compilation is done each time before you can initiate a new change. So the Hyper-Retimer is one of those stages. Thus you can stop the compile after the retimer is done, skipping the rest of the stages, evaluate the results, and start another compile for faster turnaround times. The Hyper-Retimer appears as the retime stage of the FITR in the Quartus software. It automatically runs when the FITR is executed, but you can run it as a separate stage in the UI by clicking on Retime in the compilation dashboard, or by clicking on Start FITR Retime in the Start submenu of the processing menu. You can run it separately from the command line as well by using the Quartus_fit-retime command. The other hyper-aware compilation flow feature for the Hyperflex architecture is called Hyper-Aware CAD. Hyper-Aware CAD runs as part of the fitter, during which the fitter makes decisions knowing the Hyper-Retimer will run later in the flow. Thus, the fitter can optimize parts of the design that may not be improved or may be difficult to improve by the Hyper-Retimer alone. The fitter can also optimize paths to improve the effectiveness of the Hyper-Retimer. Hyper-Aware CAD is enabled automatically when the Hyper-Retimer is turned on, so it is on by default as well. Here are some examples of Hyper-Aware CAD optimizations. The first is called long path optimization, where the fitter focuses on part of the design that will benefit less from the Hyper-Retimer. Otherwise, the fitter wastes cycles optimizing a path to get it to meet performance, only to have the Hyper-Retimer come along later and improve it anyways. With traditional timing analysis, a long path is a long path. So looking at the two paths in this first example, they both have the same long path delay. So to the timing tool and fitter, they would have the same level of criticality, and as a result, the fitter would try to optimize them the same. With long path optimization, the fitter sees that the first path actually has more registers in it. That means that there is more the Hyper-Retimer can do with this path over the path with less registers. So the path with less registers in it actually is the more critical of the two. Next is short path optimization, where the fitter can try to fix what are called short paths by rerouting or adding more routing. It is similar to the optimize hold timing option found in the fitter settings, but works specifically on paths that are eligible for retiming. In this second example, we have a situation where the Hyper-Retimer wants to reposition register number 2. In moving register number 2 to the left, the empty circles along the bottom are possible hyperregister locations. But if register number 2 was placed in either location, it would be too close to register number 1, violating the hold requirement that was discussed in the Hyperflex architecture overview online training. This path is called a short path. During short path optimization, the fitter adds additional routing to a potential short path. Adding more routing means that there are more hyperregister locations available, and the Hyper-Retimer now has valid options in which to retime register number 2. Similar to the other fitter stages, once your compilation is complete, you may review the results of the Hyper-Retimer by expanding the Retime Stage subfolder found in the Fitter folder of the compilation report. More details on specific Retime Stage reports is provided in follow-up training to this one as needed by that particular topic. Note that performance information for the design, including Hyper-Retiming results, can be found by viewing the Timing Analyzer folder or by running the Timing Analyzer tool. One report in the Retime Stage folder we do want to discuss now is the Retiming Limit Details report. As the Hyper-Retimer retimes registers to improve performance, it runs into what's called a retiming limit, or a path that it cannot improve or make faster by retiming. This path is reported back to you in the Retiming Limit Details report. This report gives you all the information you need if your goal is to run your design faster than the speed restricted by this retiming limit. In this report, you will find 3 main items. 1. The limiting reason. The limiting reason answers the questions, what is the condition that is limiting this further improvement? In other words, it is giving you the reason why the Hyper-Retimer could not get the design to run faster. Some example reasons it gives are insufficient registers, short path, long path, and path limit. These will be covered in much more detail in follow-up training. 2. Critical chain details. The critical chain is the name for the path that limits performance. This critical chain details report then answers the question, what does the actual limiting path look like? So this provides details on the specific path that caused the limiting reason. Critical chains will also be covered in more detail in follow-up training. And 3. Recommendations for critical chain. The recommendations for critical chain basically answers the question, well, what can I do if I want the design to go faster? It provides recommendations on what you can do to modify the critical chain and the design if you want to improve the efforts of the Hyper-Retimer and make your design go faster. Thus, with these three, you have all the information you need to begin to make the changes to your design and thus help your design reach its performance potential. Here is a screen capture of the Hyper-Retimer Retiming Limit Details report. At the top, you see a list of the clock domains with one limiting reason each. For the example here, you can see the limiting reason is insufficient registers. Down in the critical chain summary section, you can see the critical chain details. Similar to a detailed timing analyzer report, it lists detailed path information so you can figure out exactly why the Hyper-Retimer is reaching this limit. And then the second tab in the critical chain summary section is the recommendations for critical chain. Here you can see the Hyper-Retimer is saying that this critical chain could be retimed better if there were less delay in the path, if the path had more available pipeline stages, or if there were not asynchronous clears on the registers in the path. So, to improve the timing of this critical chain path, you follow one of the recommendations to modify the path. The timing analyzer, of course, is used to check the performance of your design, running automatically after a full compilation is complete. But you can also stop the compilation after the Hyper-Retimer and look at the performance numbers there too. Doing this, you can decide to go and make modifications to the design to improve the retiming results. To do this, when creating your timing netlist, either in the GUI or via script, you want to select the retimed snapshot as shown here on this slide. The snapshot is the state of the design database or netlist after a particular compile module has finished executing. So choosing the retimed snapshot instructs the timing analyzer to use the netlist after retiming is complete. From there, you can generate all of your typical timing analyzer reports to do the actual analysis. Be aware that the compiler's final stage has yet to run, so the software has not made any attempt to fix potential hold time issues. There is one other new compiler flow feature added called Fast Forward Compile. This feature can help with critical chain analysis and figuring out what changes you may need to make in order to improve your design performance. It will be discussed in the follow-up online training to this one called Using Fast Forward Compile for the Intel Hyperflex architecture. In this next section, we will learn about some other tools in the Intel Quartus Prime software that will help analyzing the results of Hyperflex optimizations. Here we will talk about three features or tools: the netlist viewers, the modified analysis reports, and the design assistant. To aid in design analysis and debugging, the Quartus software provides various viewer windows such as the Post-Fit Technology Map Viewer. For the Hyperflex architecture, this viewer window has been updated for designs that include hyperregisters, allowing you to view the results of Hyper-Aware CAD and the Hyper-Retimer. On this slide is an example screen capture of the Tech Map Viewer. ALM and hyperregisters that are enabled are displayed as pink blocks. The hyperregisters have the word hyper below them in text to distinguish them from the ALM registers in the viewer window. ALM registers that were enabled by the fitter but then disabled during retiming are shown as gray blocks. They still appear in the data path, but the gray indicates that the registers are no longer functioning in the design. They also show the text bypassed underneath them. More on the process of enabling and disabling registers will be covered in follow-up training to this one. Remember that routing wire segments, row and column, have bypassable hyperregisters available. Also, all block structures have bypassable hyperregisters on their inputs. Since hyperregister use is currently determined by the Hyper-Retimer and not your RTL, the software needs a way to report when hyperregisters are enabled and when an ALM register is bypassed in favor of a hyperregister. This is done by means of a special naming convention. If a hyperregister modification is performed, the names of the original routing segment or design node is modified to indicate register use or non-use. For example, if a routing segment hyperregister is enabled, then _DFF is appended to the routing segment name and displayed in the report. If a block input hyperregister is enabled, then _DFF is appended to the input node name for that block. And if an ALM register is bypassed, then tilde.comb is appended to the original ALM register name. Here is an example of a Hyper-Retimer report to highlight this. At the top, you can see an ALM register named B0R tilde duplicate. This is the original ALM register because there is not an _DFF appended to the end. In the middle, you can see that a tilde.comb has been appended to the name B0_out. This means that the ALM register named B0_out is now bypassed. So the ALM is driving out an unregistered combinational value now, and the register functionality has been moved elsewhere. Looking down further in the report, you can see a register named B_out tilde, then the name of the location of a column interconnect _DFF. This is a routing segment hyperregister that is now enabled, replacing the B0_out ALM register that was disabled above. The Design Assistant is a design rule checking tool found in the Quartus software. It uses a list of design guidelines to check your design for issues that could potentially affect its performance or its functionality. One advantage of the tool is that the rules are customizable, so you can decide which rules are evaluated and which are skipped based on your knowledge of the design. Thus, you can skip rules that you don't care about. This, of course, means that the results of the Design Assistant are customized to your specific implementation. Rules are also assigned severity levels, which can help you prioritize which checks to handle first. While the Design Assistant can be used on any FPGA design in the Quartus software, it also contains specific rules that look for issues that could affect the use of hyperregisters. This makes the Design Assistant a valuable resource for fixing performance limitations as early in the design flow as possible. You can run the Design Assistant in one of two ways: an automated mode that runs automatically during compilation, and an analysis mode that runs when the report DRC command is executed from the timing analyzer or the chip planner. The Design Assistant's rules are organized into categories such as clock domain crossing rules, rules to check on clock usage, rules to check reset connections, and so on. This table shown here displays a few of the categories and the kind of checks found in them. Based on the category, each rule is assigned an ID number. Organizing the rules this way makes it easier to find and reference specific rules. The screen capture here shows the Quartus settings window with the Design Assistant category selected. At the top of this page are filters to control which rules are displayed. You can filter by the rule's assigned ID name, the rule category, the compiler stage that checks the rule, and severity level. Once you set your filters, you can then go through the list of rules to see the rule details. Here you can select or deselect according to whether to use a particular rule. Here too you can see during which compiler stage a particular rule is going to be checked. Some rules even have additional parameters that you can configure. For example, there is a rule that flags high fan-out. So you can use its parameter to set a value above which you consider a signal to have high fan-out. Finally, there is an option on this page for you to enable the Design Assistant to run the selected rules every time you execute a compilation. Lastly, this screen capture shows an example of a Design Assistant report. On the left side are the rules that were checked during the last run. Any rule violations will be highlighted in color to indicate the severity with the number of actual instances of the violation noted. Again, use the filters at the top to limit the rules shown. Once you select a rule, the right side shows everything you need to do further analysis of the rule violation. There you have the complete list of signals violating the rule, filters to again limit which violations are shown, a detailed description of the rule being checked and a recommended solution, and links to detailed documentation if you wish to research the rule further. Finally, you can right-click on a signal in the list and cross-probe to other software views such as the design files, the RTL viewer, the technology map viewer, or the chip planner. Again, using the design assistant can really help you diagnose these issues as early in the flow as possible. This concludes our look at software features that make up the Quartus Software Hyper-Aware design flow. During this training, you learned that the Hyper-Retimer is the stage of the fitter that moves or retimes ALM registers into hyper-register locations to improve your design's clock speed. You can use the Hyper-Retimer output report in the Quartus Software compilation report to understand what you need to do to optimize even further. You learned that Hyper-Aware CAD settings allow the fitter to make adjustments assuming the Hyper-Retimer will run later in the flow. And you learned how you can distinguish hyper-register use in netlist viewers and timing reports, and how you can enable rules in the design assistant that can help you find potential issues affecting your design's functionality or performance. All of this is available so your designs can get the most out of the Hyperflex architecture. If you would like to continue in your learning on how to design for the Hyperflex architecture, please view the free online training using Fast Forward Compile for the Intel Hyperflex architecture. Intel provides multiple avenues in which to learn about Intel FPGA products. There's the Intel FPGA YouTube channel, which contains 5-minute quick videos along with longer, more in-depth training videos. There's the Intel FPGA training website where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses even with labs and demos. Lastly, you can enroll in a live instructor-led course presented either in person at an office local to you or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages called landing pages dedicated to specific FPGA technology like external memory interfaces and high-speed protocol interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA applications engineers. The Intel FPGA training team is always looking to improve our material. To do this, a survey will be emailed to your registration email address. We welcome any feedback you may have. This concludes this online training. Again, my name is Marlon Price, and I thank you for attending.